Hi everyone and welcome to the video on standardized scores and the 68, 95, 99.7% rule. So what I'm going to be doing today is having a look at normal distributions, and you can see I've already drawn a couple of them here and just seeing how we can apply them and solve problems with them. So first thing you might notice is this right here. Okay, might look a little bit intimidating, but this is just a way of describing a normal distribution. So it's saying X is a normal distribution with a mean of 30, so this part right here is the mean, and a variance of 25, so that's sigma squared is equal to 25. Remembering that that's the variance, that means that the standard deviation is just going to be 5. So over here we have Z as a normal distribution with a mean of 0 and a variance of 1, which means that the standard deviation is also going to be 1. Now, I hope that you appreciate just how long it's actually taken me to draw these up to make them look roughly symmetrical and all that. It's been an absolute nightmare, but let's get stuck into it. So what I'm going to do is I'm going to draw this distribution on both of the graphs. So the first one, we've got the distribution in terms of X. It has a mean of 30. The mean always goes in the middle. And a standard deviation of 5. So it's going to go to 35 and then to 40. And then to 45, making sure to have nice even spacing along the axis. And then we can also go in the negative direction as well. So we could go down to 25, down to 20, and then down to 15. And if we draw it for the normal distribution, then we've got a mean of 0, and it goes to 1, to 2, and to 3, and down here to negative 1, and negative 2, and negative 3. They do go further in both directions, but you know, we have most of our scores falling in this area, so we don't sort of usually worry about drawing it much further out than that. And this is, you know, really just highlighting that these two graphs, we can change between, you know, one and the other fairly easily. You can see that they have the same shape, and you can see that a score of 35 on this graph here would correspond to a score of 1 over here, or a score of 45 here would correspond to a score of 3 over here. So what I've done here is I've normalized the data, and the calculation of the Z-score is actually quite an important one to be able to do. And the reason for that is that Z tells us how many standard deviations a score is from the mean. So a Z-score of 2, for example, means that the result is 2 standard deviations above the mean. Whereas a Z-score of negative 3 means that the score is 3 standard deviations below the mean. So coming back over here, we can see that this score of 15 is 3 standard deviations below the mean, which we can count out because we know the standard deviation is 5, so it's going 1, 2, 3 standard deviations below. Before I go any further with this video, I probably should mention how to calculate Z. So to calculate Z, we do the actual score minus the standard deviation and then divide it by sigma. So the reason that works is because we're doing the difference between the score and the mean, and then dividing it by sigma. So that's going to tell us how many of those standard deviations actually go into that difference. And the last thing I'll mention in this video, just a moment. Alright, sorry. The last thing I'll mention here is that we need to also look at the 68, 95, 99.7% rule. And all that means is that within one standard deviation of the mean, so from here to here, we actually have 68% of all of our scores. So, you know, I can draw that as an interval like this. So that's 68% of the scores. Within 2 standard deviations, so from here to here, we have 95% of all scores. And within 3 standard deviations, so that's going from here all the way across to here, we have 99.7% of all scores. And obviously we can do all these symmetrical calculations. Anyway, leave it there. See you guys.